All right, scholars, welcome back. Like I had mentioned in the previous video, we are starting to delve deeper into more statistical based content. So fasten your seatbelts. The ride might get a little bumpy. Today we're going to be learning to identify normal distributions as a way to model distributions that are approximately symmetric and bell-shaped. So I can calculate a relative frequency and create a relative frequency histogram. I'll know I've got it when I know that a normal curve is defined using the mean and standard deviation. Let's begin. Okay, in the following histograms, a group of 500 healthy people who had their temperature taken. 3 histograms represent examples of data that approximate a normal distribution, and 3 histograms represent non-examples or data that do not approximate a normal distribution. What do you think the elements are of a definition of normal distribution? So zooming in, okay, we can clearly see that there are some similarities between our examples, and then there are definitely some drastic similarities between our non-examples. So take a look, let us know what you think are the elements for the definition of a normal distribution. We define a normal distribution to be a specific distribution of data and statistics that is symmetric and bell-shaped, as evidenced here. And it has an area of 1 between the x-axis and the curve. So all of this space here, if I was able to take like a crayon and color in between the lines, it would have a total area of 1 with the x-axis serving as a horizontal asymptote. Distributions that are approximately bell-shaped and symmetric can often be modeled by a normal distribution in a similar way to how scatterplot data could be modeled with a line or other curve. A normal distribution is determined entirely by the mean standard deviation for a set of data. That's what determines how the data is spread out about the mean. And the apex of the curve would be the location of the mean or the average. So here we have a manufacturer of butter, makes sticks of butter that weigh 110 grams on average. Manufacturer suspects the machine that forms the sticks of butter may have a problem, so they weigh each stick of butter the machine produces in an hour. The weights are grouped into intervals of 0.5 grams and are summarized in a frequency table and represented graphically by the histogram. Knowing that we have a certain amount of data and the frequency in which, right, we have a total of 1,171 sticks of butter whose weight was measured, and a specific frequency based on the weight of that stick of butter. Calculate the relative frequency for each weight interval. The relative frequency for the total would be 1, right, which represents the area under the curve. If you are not sure what the relative frequency is, the relative frequency is nothing more than the frequency of that particular interval divided by the total number of values. So I'll spare you the trouble here, but read through this. Relative frequency histogram is a histogram in which the height of each bar is the relative frequency of that interval. So since the heights of the bars are found by dividing each height by the total number of the sticks of butter, the shape of the distribution is the same as the regular histogram. Labels on the y-axis are changed. So I would like for you to label the y-axis accordingly and indicate on our relative frequency histogram the bars that correspond to the sticks of butter that are more than 1 gram away from the intended weight of a stick of butter. Should this machine be replaced, explain or show your reasoning. So in order to even answer these questions here, you must first complete this table accordingly, because that will inform you as to what sticks of butter are more than 1 gram away from the intended weight. Remember, the intended weight is located here, 110 grams. Okay. You can draw a little line if you'd like to designate, right, that those values are more than 1 gram away, if that's what you think. Here, we're kind of simply getting our feet wet, for lack of a better word. So we have these curves that represent normal distributions. As I had mentioned earlier in this video, a normal distribution is defined entirely by the mean and standard deviation. So based on these 5 images, what do you notice? So although it's difficult to see in these graphs, the x-axis is considered a horizontal asymptote. For normal curves, as you follow the curve to the right or left, the curve gets closer and closer to the x-axis without ever actually touching it, right? And it almost looks like it does, but trust us, it does not. Normal curves are bell-shaped and are most reliably used to model bell-shaped or approximately bell-shaped distributions. The area under the normal curve is always 1. When the standard deviation increases, the curve spreads out to the right and left, right? It flattens. To maintain the same area, the height of the peak must decrease. And vice versa, if the standard deviation decreases, meaning there's less variability in the data from the average or the mean of the data set, so the data should be much more compact, that would make the height of the peak increase, right? So we would kind of have relatively tall normal distributions, as you can kind of see in especially our standard deviation of 0.8. It looks to be the most narrow of our normal distributions. So jot down some things that you notice, and based on that image, what do you think the normal curve for a larger standard deviation is wider and shorter than one with a, or why do you think the normal curve for a larger standard deviation is wider and shorter than one with a smaller standard deviation? And what is the shape of the normal curve? If you watch this video, those questions should be very straightforward. See you in class.